These are my contents of my topic. So basically, striking fault is a fault on which most of the movement is parallel to the fault of the strike. Basically, these are the range zones along which two arranged blocks move sideways horizontally parallel to the strike of the fault. Striking fault occurs in from hundreds of meters to the thousands of kilometers scale in globally. And here, few examples: the San Andreas fault in California, North Anatolian fault in Turkey, and the Great Sumatran fault in Indonesia. In the past diagram, we have the range regime, also known as the strike slip regime. Here we can, as we know, the principal stress axis, that is sigma 1, and the least minimum stress axis sigma 3 lies horizontally, and the intermediate sigma axis, that is the intermediate compressive stress axis, that is sigma 2, remains vertically. And according to the movement of adjacent block, we have two kinds of strike slip fault. One is the distal, also known as right lateral strike slip fault, and another is the occipital, known as left lateral strike slip fault. So, fault branching refers to the process where a primary fault splits into two and more secondary fault lines. This branching occurs due to the complex stress conditions within the arc crust, causing fractures that deviate from the main fault path. Polyakov and Kame have shown that the propensity of the rupture path to follow a fault branching is determined by the three conditions. One is the pre-existing stress state, and another is the branch angle, and the last one is the rupture velocity or branch location. So here we have some global examples where we have branching in the fault. The Imperial fault branched into Crosby fault, and Johnson fault branched into Chicago fault, and in the last one, the Devon fault branched into Toshunda fault. And here Kame uses these three parameters to explain the model of fault branching. Here the x-axis denotes the strike of the main fault, and S-max denotes the maximum compressive stress direction. And psi is the angle between maximum compressive stress direction and the strike of the main fault. And here the branching of the fault that will occur. And the phi is the angle between the branch fault and the main fault. The strike of the main fault. And here the quadrant 1 is known as the compressional side, and quadrant 4 is known as the extensional side. The inclination of psi angle denotes the branching will occur in the compressional side or the extension side. When we have the high inclination of psi angle, the branching will occur in the extension side, and when we have the less inclination of psi angle, the branching will occur in the compressional side. Marked by the shaded region. And here we have a range of psi angle from 56 degree to 13 degree, and here you can see as the value of psi angle decreases, the branching moves from extension side to compression side as well. In case of 56 degree, the branching is more in the extension side, and in case of 45 degree, the branching is in between the compression side and extension side, and in case of 25 degree, the branching is more in the compression side, and in case of 13 degree, the branching is complete in the compression side. And here we have another case when the psi angle is very less, and then there will be no fault branching, there will be fault parallel extension. And in this line, the rupture velocity that determines the nucleation zone. Here, this line indicates the nucleation. This line indicates the intersection point of the fault branch, and this black line indicates the nucleation zone. As we can see, the rupture velocity gradually increases from 0.6 to 0.8, then to 0.9. And with respect to increasing rupture velocity, the nucleation zone moves away from the intersection point. And here we have branching angle. In case of compression, the branching angle is considered as the positive, and in case of extension side, the branching angle is considered as the negative sign. And this determines the branching will be more wide or narrow. When we have the branching angle more than the 30 degree, the branching will be wide. In these two cases, we have the high angle more than the 30 degree. And when the branching angle is less than 15 degree or less, the branching will be narrow. We can see these two diagrams. Now let's come to the Lee-Wittney-Rubin law. Basically, this law describes the shear stress tau is the function of the normal stress, and here tau p determines the maximum peak shear stress during the branching of the fault, and then you indicate the sleep of the fault. As the fault has been branched, here we have the maximum shear stress, that is delta P, this is tau P, and it increases linearly with respect to sleep of the fault. And here we have tau I, that is also known as the residual shear stress. And it affects the DC, the critical value, where afterward there will be no propagation of the branch fault, and it determines the termination of the branch fault. And we have three modes. When in mode 1, the branching will be occurring in the both main fault and branch fault, and in mode 2, the rupture will be occurring in the branch fault, and in mode 3, the rupture will be only in main fault. And in the right side there are respective examples. Now coming to the subsidiary factors or literature, basically these shears are these shears result from the before the branching of the fault as a part of the initial stage of deformation in the principal deformation zone. In this diagram, you can see the P dash, R dash, and P, Y, and R are the subsidiary shears. But among them, P, Y, and R are the further synthetic literature, which form with acute angle to the strike of the fault. And R shear is supposed to form first, and the Y shear is supposed to be formed in the last. And the Y shear always remain parallel to the strike of the fault. With respect to synthetic fault, the antisynthetic fault, that is P dash and R dash, will form to balance the system, and always the antisynthetic forms with high obtuse angle nearly equal to 75 degrees to the main fault. And in this diagram, the yellow zone marks the tension gases. Basically, tension gases are the shearing zones. Tension gases form when shear cracks propagate and open at their fields. They are formed in areas of stress such as during strike arcades. Tension gases are used to determine the type of shear zones, assess strain localization, and determine the stress axis that form the tensile shear zone. They can also indicate the presence of favorable conditions for oil and gas accumulation. Now coming to the rupture directivity. Rupture directivity refers to the direction in which the fault rupture propagates during an arcade. It can amplify seismic wave leading to the more intense ground shaking in certain areas. The rupture zones of major arcades often involve geometric complexities including fault bands, branches, and stakeholders. In case of acute angle branching, we can determine or predict the rupture directivity. But in case of obtuse angle branching, we cannot predict the rupture directivity, and also the obtuse angle branching is not favored by the stress field. But in certain field observation, the rupture path seems to be branched through highly obtuse angles and looks like as the branching has been occurred in the backward direction. But actually, as we discussed the case 1 where the branching will occur in the active angle. And in these conditions, we can predict the rupture directivity. But in case the obtuse angle branching, where the branching occur with high obtuse angle, we can, but it never becomes and absolutely impossible. But what happened there comes the jumping mechanism. When the nucleus of one fault propagates to the nearby fault and moves backward. And it is the example of 1992 standard earthquake where the Johnson fault has been branched into Kikava fault, and in reduction is that the Kikava fault which is branched with highly obtuse angle with the Johnson fault. And we can predict the earthquake epicenter from the fault branching. When we have unidirectional branching, if the branching has been occurring in the one end, then to the opposite end, the epicenter will be earthquake lies. And when we have the branching at two sides of the fault, then the epicenter must be in the middle or somewhere in the mid portion of the fault. Fault branching is primary fault, and rupture directivity are critical factors in understanding earthquake mechanics and associated hazards. Rupture directivity, where seismic waves are focused in the direction of rupture propagation, can significantly amplify the impact of regions located along the fault strike. Together, these phenomena highlight the complexity of fault systems and need of different geophysical studies to assess seismic reserve accurately by integrating advanced modeling, field observation, and empirical archive data. Researchers can better predict the behavior of seismic fault and mitigate the risk associated with the future seismic events. And these are my reflections. Thank you.